Welcome everyone. Thank you for joining us today and welcome to Astro 3D ECR Astronomers in Australia seminar series. My name is Anisha Harshan. I'm from the University of New South Wales and I'll be chairing today along with my co-chair Dr. Jeffrey Simpson, also from University of New South Wales in Sydney, Australia. Before we begin, it's important for us to acknowledge the traditional custodians of the land on which we meet today, the Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing systems of knowledge on which we continue to build. We acknowledge the traditional custodians of the unceded lands on which we are meeting today. I'm speaking to you from the land of Bedegal people. My co-chair Jeffrey is joining us from the land of Wallumedegal clan. Our first speaker, John O'Gannon, is speaking to you from the land of Wurundjeri people of Kulin Nation. And our second speaker, Nickolas Pingel, is speaking from Ngunnawal country. We pay our respects to their elders, past and present, and extend their respect to First Peoples joining us here. So while we're here, this series is facilitated by ASTRO 3D, which is Australian Research Council Centre of Excellence for All Sky Astrophysics in 3 dimensions. Of course, COVID-19 has affected our ability to travel and present at international seminars this year, and especially for us in Australia due to our time zone constraints. So this series was created to provide opportunities to early career researchers in Australia to reach an international audience and to try to mitigate that disadvantage. Before we begin, I'd just like to mention that there will be 2 talks over this hour. Each talk will be 20 minutes in length and about 5 minutes for questions at the end, which will be chaired by Jeffrey. So I would please ask you to save your questions until the end of each talk. Of course, feel free to use the chat function to ask your questions if you prefer, and Jeffrey can read them out to our presenters at the end. I would also ask you to not talk unless your name is being called upon. Of course, these talks will be recorded and will be placed afterwards on the Astro 3D's YouTube channel. And by being here today, you are agreeing to abide by Astro 3D's meeting code of conduct. I've already warned the speakers about this, but just to state again, due to limitations of Zoom, I will have to interrupt verbally to indicate the 5 minutes mark to the speakers. The next talk is by Nickolas Pingel, who is a postdoctoral researcher at the Australian National University. Nickolas's interest is in using high angular and spectral resolution GASKAP data to characterize the turbulent properties of the nearby neutral hydrogen and investigate links to other ISM traces. Take the screen. Thank you.
Okay, thank you very much. So good morning, everyone. My name is Dr. Nickolas Pingel, and actually greeting from Cairns, Australia, where I'm currently on holiday, but I'm still very excited to be speaking with all of you. Yesterday, my wife and I scuba dived the Great Barrier Reef, which was amazing, so I highly recommend coming down to Australia when you get the chance, when they open international borders at some point. No, but I will say that I'm in a hotel lobby, so I apologize for any background noise you might hear. Hopefully it's not too distracting. But yes, I'm a postdoctoral researcher where I work with Professor Naomi McClure-Griffiths at the Australian National University. Today, I'm very excited to be presenting some of the new and exciting results of our pilot observations of the Galactic ASKAP Survey, or GASKAP Survey, which covers H1 observations of the Small Magellanic Cloud, the start of the Magellanic Bridge towards the LMC, and the Magellanic Stream. And I'm hoping by the end of this talk, you'll be convinced about the power of ASKAP telescope and phased array feed technology in general. So ASKAP, or the Australian Square Kilometre Array Pathfinder, is the 36-element interferometer that's located in the Murchison Radio Astronomy Observatory in Western Australia. Its most unique feature is that each antenna is outfitted with a phased array feed receiver, which expands the instantaneous field of view from 1 square degree to a whopping 25 square degrees, and they do this by forming 36 simultaneous primary beams on the sky. Now, each path or phased array feed consists of 188 individual detecting elements, so they work in conjunction to form those 36 primary beams. Beamforming from a signal processing perspective is basically taking the signal from each sensor element on a path, digitally sampling it, and then multiplying it by a complex weight. From a sky perspective, each element has its own kind of view of the sky, and it illuminates the dish in a certain way. One can imagine that there's a set of weights that will optimally manipulate the response of each one of these dipoles to form a desired beam. The final beam will then be a linear combination of the weighted responses and can be placed anywhere within the instrument's field of view. So this is what our particular observing path footprint looks like. So typically from a single element interferometer with a single pixel receiver, you would just form one of these beams. With ASKAP, you're getting 36 of them all at once. Now, the increased field of view translates into increased survey speeds, and ultimately that means an order of magnitude increase in sensitivity. This gives astronomers the opportunity to create truly unprecedented data sets of the neutral hydrogen and OH in both the Milky Way and the Magellanic System. And these are, of course, perfect laboratories to study gas dynamics. So, for example, the feedback processes, accretion onto the Milky Way, the interaction between individual clouds, also the bridge, the stream, and the Milky Way itself. We can also use it to measure H1 emission and absorption in conjunction in order to study phase changes. And my primary scientific interest is to, for the first time, utilize this unprecedented angular and spectral resolution to characterize the turbulent properties of the H1 at similar scales to the other traces of the interstellar medium, such as molecular gas and dust. Specifically, I'm looking to observationally measure the energy injection scales into the ISM, which we could then relate back to predictions from, for example, models of star formation and informed stellar feedback models. Our full survey, which will hopefully start within the next 2 years, will have 3 components where we'll cover the Magellanic clouds and really focus on that region to get the most sensitive areas of our survey. We'll then focus on the low latitude, so this extends upward of 2.5 degrees above and below the main plane of the Milky Way, and then extend upwards to the intermediate latitudes that goes up to plus and minus 10 degrees. Now, for our pilot survey, phase 1, we were awarded 80 hours for fields that are representative of what we will observe for the full survey. Our main goal was to select fields that will push our processing capabilities, which I'll talk a little bit about in the next few slides. Of course, probably the most scientifically interesting field is the galactic center, but is one of the most difficult fields in the sky to process due to the immense amount of continuum that's in the field. But by starting with the most difficult field, we can inform and kind of tweak our processing capabilities. Now, unfortunately, we believe that these observations were affected by firmware limitations of the telescope that have since been fixed, but we're finding it difficult to calibrate this field, but we're hoping that we can get a chance at it in the near future. But we did observe a field in the galactic plane, so this gives us a slightly easier low latitude field to process if the galactic center observations initially proved too challenging. The resulting images are looking very promising, and I'm going to show off I'm going to show off just a quick preview of this data set, but it's still being processed. So following also successful zoom observations of 2 adjacent fields, we continued observations on the SMC and obtained similar observations of the Magellanic Stream and Magellanic Bridge. So we can extend our high resolution view of the H1 associated with the Magellanic System. Now, this is where I'm going to show off the power of phased array feed technology. So let's take a look at some of the new data. So previous observations of the SMC that were done with the Australian Telescope Compact Array and Parkes, this is about 20 years ago in 1999, had to do individual pointings across the entire field of the SMC. And so this made about 320 individual pointings. And so it took quite a while to do these. It's a very nice image, but it just took a long time to make. Now with ASKAP, we're actually able to cover the same area in a single pointing, and we can increase the field of view from 1.7 arc minutes down to 30 arc seconds. So I think this is one of the most amazing examples of the power that ASKAP has in terms of how quickly the survey speeds actually are with the telescope. Now, of course, with the new technology comes with new challenges. So typical full field ASKAP images are produced in such a way where you deconvolve the image from each individual beam. And so deconvolution is just removing the inherent point spread function response from the sky brightness distribution. So both surveys will just do this and process a single beam and then stitch that image together to make a final image. So this works for almost all other ASKAP surveys, as the emission is very small scale. So for example, a single galaxy that's far, far away, where all the emission is contained within a single beam. So this does not work for the H1 emission that we're targeting with GASKAP, because generally this H1 emission extends over the boundaries of multiple beams. So that's demonstrated in the figure here where I've overlaid the beam centers. So what I've had to do is utilize an imaging method called joint deconvolution. So this is where we take we make a single large image from all the measured visibilities from the telescope, and then we move on to the deconvolution of this single large image. Now, unfortunately, this is immensely computationally expensive, such that the main processing cluster that's used for ASKAP data in Perth does not actually have this sufficient core node memory to do this. So the capability to run joint deconvolution is not supported on their main processing cluster, and it's also not even supported currently in ASKAP Soft, which is the main software suite to reduce and image ASKAP data. So we are testing improvements to this, but currently that mode is not available. So as a workaround, what I've done is wrote a custom pipeline that utilizes the Common Astronomy Software Package, or CASA. And this, I'm just showing a little bit of this pipeline that's hosted on my GitHub. It basically consists of a series of CASA configuration scripts that you can set to do various things that you want to do with your data, such as like bin the data, UV-based continuum subtraction, and of course, image the data. It mainly consists of control scripts that are written for both Slurm and PBS control, depending upon what your cluster calls for. And this is where you can set your specific cleaning parameters, such as your total iterations, the noise you want to clean down to, etc. The jobs are then submitted as a series of batch jobs, and it's distributed across a computing cluster to image the data as efficiently as possible. We image each channel individually, each spectral channel of the data cube individually, to ensure the memory is managed in a reasonable way, because things will slow down very quickly if you're trying to image multiple channels. So usually I find that 20,000 iterations and with major cycles triggered every 2,000 minor cycle iterations usually gives a decently deconvolved image. The total time to image a single channel is about 6 hours, but this can extend up to 15 hours if the emission is very complicated. But currently, this is the only pipeline that's able to run joint deconvolution in a distributed manner across a cluster. While CASA gives good results, I have had recent success using another third-party software called WSClean. This is much more optimized. It's written in C. So we're hoping to implement a similar pipeline for the full survey. Okay, but let's get to some actual data to show off. So this shows the peak intensity image. So basically the brightest pixel along the spectral axis of our data cubes. And Jonah showed a nice figure in his talk that showed an IFU data cube. It's kind of the same idea. So what we're doing here, this field is centered on the Magellanic stream. And we're cheating here a little bit because we've only showing this significant signal, but it gives you a sense of kind of the amazing detail that's provided by GASKAP. So there's a plethora of small scale structure, as you can see in this image, that takes the form of discrete clouds. You have arcs and filaments and head to tail like clouds. This indicates stripping from ram pressure. Overall, we're seeing a very complicated exogalactic network of discrete clouds that also move at anomalous velocities. Here is the same field, but in the context of the SNC. So you can see just how large our field of views that we're getting with this is. This is a peak intensity image of the Magellanic Bridge, which probably is my favorite image to come from the entire pilot phase 1 survey. So again, we're seeing a wide range of structure at all scales, and very, very enticing and interesting filamentary structures on the scale of the synthesized beam. So to give you a sense of the physical scales that we're probing here, it's about 8 parsecs, assuming the same distance to the SMC. And as promised, here is a peak intensity image of the galactic plane. So this data is still being processed, but gives you a sense of also the filamentary structure that we're seeing in the data. This is very interesting because given the work with Susan Clark, where she was able to measure the orientation angle of these H1 fibers, relate them back to polarized starlight data, you can see and trace the magnetic field in the H1. So this is just the data cube, GIFs of the data cube stepping through, and you can see, so the right is the SMC, on the left is the Magellanic stream, and it just gives you a sense of all the structures that you see at anomalous velocities. One thing to focus on is on the stream at around 205 kilometers a second. It's coming up. You can see this long filamentary structure here that kind of pops up. And this is resolved over only 10 kilometers a second. And if you assume the same distance to the SMC, it's about 50 parsecs wide and almost upwards of 850 parsecs long. So that's kind of just amazing what we're seeing with these data. And there's just, the field of view is very large. It's very exciting to jump in and see. Now, the Magellanic fields reveal an extensive network of H1 features that extend upwards of about 2 kiloparsecs from the main body of the SMC. So some of these have been highlighted already by a Nature Astronomy article written by Naomi McClure-Griffiths, and she used a test data set of the SMC when ASKAP only had 16 antennas and also 5 times worse spectral resolution. Now, the increase in angular and spectral resolution and sensitivity allows us to really focus on these extraordinary features. So I've highlighted a particularly interesting high velocity cloud here. So the increased angular, in addition to better understand of the kinematics of these discrete clouds, we can provide a much more accurate estimate of the H1 masses and total flux profiles. So you can see this with the test data set in orange and the pilot data set, you can see that the flux profile is much more resolved. And you can see in the individual channel maps, there's a distinct shell-like feature in the first kind of 6 panels here that was unresolved spectrally in the test data set. Looking at the measurements of the expansion velocity of the shell-like feature, we are able to get better constraints on the expansion velocity, and we've determined that an OB type star is the likely source of the shell, though comparisons with Gaia data is inconclusive in terms of a smoking gun detection of the young stellar cluster. But hopefully with the updated release of the Gaia data sets with actual distances, we'll be able to constrain this further. Overall, what I'm trying to say about these particular data sets and the population of high velocity clouds is that an improved model of the SMC kinematics will be able to subtract off the bulk emission and catalog a whole new population of clouds that move at anomalous velocities, not only SMC, but eventually the LMC as well. So as I mentioned in my previous slides, my main interest with GASKAP is to use known and refined statistical diagnostic tools to characterize turbulence environments across the Magellanic System and the Milky Way. So turbulence is essentially the nonlinear motion of a fluid that is excited over a wide range of correlated spatial scales, and it has immense influences on the properties of the ISM. So it is driven on large scales, and it will cascade down to affect properties at large scales, small scales, such as star formation. So one specific example of this is star formation efficiency, so basically how much gas will end up at stars. This is observed to be 1 to 2%, but it should be much higher, and this is likely because it's regulated through turbulence in order to counteract the gravitational collapse. There are many 3-letter acronyms here that I've listed that exist to diagnose and characterize turbulence. So many studies apply these, but few have really provided analysis in the context of the multi-phase ISM. So for example, looking at CO, H1, and dust in conjunction with one another. So I'll spend the rest of my time discussing a specific tool called the Spatial Power Spectrum, or the SPS, which can be applied to observational data to constrain the full 3D turbulent energy spectrum of the ISM. So the density distribution of the ISM is influenced by the random nature of the underlying velocity flow, so the turbulent flow, and it's characterized by a power law. The SPS is a tool to measure the underlying power law, which we can then compare to models of incompressible and compressible gas. Because the power spectrum and the 2-point autocorrelation function are basically for a transform pair, it essentially measures the amount of structure at a given scale. So in practice, we compute the power spectrum by taking the absolute value of the Fourier transform of an image multiplied by its complex conjugate, which is the equation below. And then we measure the median power as over a range of annuli overplotted on this 2D power spectrum image. And we use the median because it's robust against bias from the Gibbs ring phenomenon, which is basically caused by taking Fourier transform of something with a discrete edge.
Sorry, Nickolas, that's the 5-minute round for you.
Great. All right. Thank you. So the underlying power law is given by the slope of the SPS and can provide important properties of turbulence, such as the energy injection and dissipation scales. So this is usually seen when the power law slope changes. And so with H1, this is usually not resolved in observational data, but I really do think ASKAP can help us probe this regime. But if we have a steep slope, this implies that most of the structure exists on large scales with virtually no power at small scales. So this can happen in regions where there's little to little or no star formation that produces small scale shocks. On the other hand, if you have a shallow slope, this implies structure on small scales that might be due to shocks caused by stellar feedback mechanisms, or even the direct detection of a clumpy cold neutral medium in the cases of CO and molecular gas. So what can our new fantastic GASKAP images really reveal about turbulence in the SMC and Milky Way? So to measure power law index, what I've done is I fit a single component power law model to each of the spectral planes in the ASKAP and older compact array cubes of the SMC. So the examples of the spectrum profiles from a representative channel are shown in the plot below. And the first major difference that you might notice is that the overall shapes are very different. So this is caused by the increased angular resolution, meaning that the power at the small scales in the ASKAP data must be disentangled for the drop in the PSF response of the radio telescope. So this can be accounted for by forward modeling the synthesized beam, where I've multiplied the power spectrum by the power spectrum of 30 arcsecond Gaussian. And I've also included an additional scaling factor for the noise to account for the influence of noise at small scales. So amazingly, what we see is that the slope of the ASKAP data is much, much shallower than the compact array. So these shallower slopes are comparable to what we actually see in molecular gas and CO, and also self-gravitating mediums. So this implies, in fact, the density fluctuations of H1 at these previously never before resolved spatial scales may be driven by similar processes as CO, or we might be detecting the cold neutral medium. So to test this, what I've done is to see if we've been actually detecting the effects of stellar feedback, such as shocks. I've repeated this analysis for subregions of the SMC. So for example, the bar, which is this solid rectangular region in the center here, hosts the most active regions of star formation in the SMC. And you see that it has much shallower slopes over a wide range of velocities relative to a more quiescent region of the so-called wing, which is this dotted rectangle over here. And this extends towards the LNC. So this suggests that indeed the shallower slopes of the power spectrum are indeed caused by the newly detected shocks and compressions that are related to stellar feedback. So this is exciting because this is direct detection of these properties in H1. And also interestingly, the spectral indices of the bar trace the indices fit for the entirety of the SMC. So I think this again just shows that the overall shape of the power spectrum is very influenced by the presence of small scale structure. And this agrees with theoretical work such as Burkhardt et al. 2015, where the inclusion of self-gravity and MHD simulations of the ISM have seen very shallow power spectra. And for most importantly, for the first time, we are tracing the turbulent and really the general properties of H1 at the same scales as the already existing spectacular images that we have for the molecular gas and dust. So just to summarize, so the main focus of the first half of my postdoc has been designing custom imaging pipelines that utilize joint deconvolution. And I have done new tests with another third-party software that's showing very promising increase in speed and more sensible iteration control to make better images with better fidelity. We have galactic plane and galactic center fields that are currently being imaged that should reveal, especially the galactic plane, something very interesting about the magnetic fields that pervade the Milky Way. The phase 2 of our survey is imminent, and this will focus mostly on connecting the fields we have from the Small Magellanic Cloud towards the LMC. And really my takeaway message is that for the first time, GASKAP provides an equivalent view of H1 at the similar physical scales of molecular gas and dust. And I really do think that GASKAP will provide really the next standard for the H1 and OH observations of both the Magellanic System and the Milky Way for the next decade, and will be one of the most utilized H1 data sets for the next decade. So I'm very excited to be working on it, and I'm also very excited to take your questions, so thank you.
Thank you, Nickolas. Do we have questions? You can raise your hand or use the chat function to type a question. I'll ask a question while we wait. I was interested in the, I guess, stellar optical follow-up on these clumps you were seeing. Is there much effort on this? Because I was interested, because Gaia sort of jumped out at me because I do stellar things, and I was curious about the sort of what follow-up goes on in the optical.
Right. So let me just go back to that slide. Yes. So what I did was basically select, just take Gaia. I think it's DR2 is the most recent data release. Yeah. And made a cut for brightness. Just to try to select very bright, very young stars to see if there was a stellar cluster that matched towards the center of the shell. And there are a lot of detections, but they exist across the whole field. And I think we have to wait for the distance measurements to be released in Gaia, which I think is upcoming. But I think that would be the next step in this type of analysis, if we can pin down the distance of these stars to see whether or not.
Yeah, I would assume that the parallax, because the parallaxes to the LMC and SMC are basically going to be 0, and so they may not be that useful, but they will help. You'll be able to throw away a lot of things that are clearly too close.
Right. Yeah, that was the problem. I think it was that we're seeing just a lot of foreground in this particular field.
Jonah has a question.
Hello, great talk, I really enjoyed it. You say that you're now imaging the gas in the same scales as the dust and the molecular gas. I was just wondering how conjoined and how related we expect the different kinematics to be of these. Obviously, they're very different grain sizes and masses, and so.
Yep. So for example, this is a paper, this is just an extra slide done by a colleague of mine, written by Enrico Di Teodoro. So he detected with apex molecular gas in some of these outflowing clouds. Specifically, I think I was focusing on this cloud earlier in the talk. And we do see that CO match spectrally with the H1 for individual clumps. And so I think this is kind of going to be the bread and butter, is basically looking at all the data, looking at apex data for the molecular gas, looking at the spectrum, how well they match spectrally and spatially, and then that will inform more properties. So the reason that this is important is because the H1 with previous test data sets for ASKAP, I think the highest spectral resolution was 4 kilometers a second, but now we can get down to about 0.25 kilometers a second. So this is very comparable with what you see with ALMA and APEX. So this is how we'll target these individual clumps in the future.
Thank you.
Great.
Also, Joda, I enjoyed your talk. Thank you as well.
Are there any other questions from the audience? If not, we are great on time. Thank you, Jonah and Nickolas, for your great talks. These talks will, of course, be uploaded onto YouTube very soon on Astro 3D's YouTube channel. Our next seminar will be at the same time in 2 weeks. Next week on 20th May with Sabine Belstad and Piyush Chadha talking about star formation in metallicities. And we hope to see you all there. Thank you.